Now let's get point. Guys, we have a very tight schedule, so I kindly ask you to slightly propagate to the place and so we are moving to the next session, which is about quantum fields and quantum algorithm from the related to the groups what we have. And let me introduce the first speaker, who is Zoltán Kolarovszki from our institute and from the Eötvös Loránd University. There with Zoltán Szimborás, who cannot be here at the moment, but Zoli will speak about the Piquasso simulation of photonic. We'll try to remove the phone from the same radio device. Okay. So simulation of photonic quantum computing with automatic differentiation in Piquasso. So the stage is yours.
Thank you. Hello, I'm Zoltán Kolarovszki. I'm a PhD student at the Eötvös Loránd University, and I also work at Wigner as a junior research fellow. And today I will talk about Piquasso and its automatic differentiation capabilities. It is a photonic quantum computing simulator framework. But first, I want to talk about photonic quantum computing. So it was previously mentioned that it is a bosonic quantum computer. It stores information as in independent optical modes. As you can see here, these are the quantum light sources. So it enters the photonic quantum computer. It goes through some optical processes implemented by some photonic quantum gates. And then at the end, there are some detectors, here in this case, single photon detectors. So that's the basic principle. And with this machine, the quantum information group at USTC demonstrated a quantum advantage over classical computation in 2020. And they repeated them or improved these experiments in 2021 and 2023. And the latter article mentioned our classical benchmark for a classical comparison, for a comparison. And there was also another quantum advantage demonstration by Xanadu. They did it with a different device. It used time multiplexing in 2022. And they used the Borealis chip, which is also publicly available. So that is great. So why do we need to simulate this? We need to simulate photonic quantum computers because they are still not widely available. So it's not available for most researchers and not available. There are so many gates in photonic quantum computers which are not available. So we want to experiment with it. It can also aid circuit design. It can also improve classical algorithms if we try to simulate it. It can be used to certify hardware, for example, the hardware for the quantum advantage schemes. And it can also help photonic quantum machine learning research via automatic differentiation. However, it is classically hard in general. So basically, that's the reason why we're doing it, because if it wouldn't be, then we wouldn't do it. So it's really difficult to do efficient simulation of photonic quantum circuits. So that's why we built Piquasso, which is a framework for simulation of photonic quantum computers. We wanted to have a simulator which we can improve and experiment with it by ourselves. And the main goal of this is extensibility. For example, we can use not just NumPy or Numba, but TensorFlow and JAX. So these are common machine learning frameworks, and we can use, or it also has a high performance. For example, with the C++ Piquasso Boost plugin, it can also be reproducible, and it also has clean code as far as I'm concerned. And Piquasso is also open source. It is available on GitHub, and you can simply install it with pip install Piquasso. So that's that. There are several available simulators in Piquasso, because if you want to simulate a photonic quantum state, then you can choose from different representations, and depending on the scenario, you want to have different states for your simulation. So, for example, you can choose the Gaussian simulator, which simulates Gaussian states, and you can have the sampling simulator, which simulates the boson sampling scheme, and the Fock and the pure Fock simulators, which simulate a more generic quantum states, but these are much harder. And there are also available simulators in the Piquasso Boost plugin. So the Piquasso Boost plugin implements the Gaussian simulator, which is called a boosted Gaussian simulator. It has been re-implemented in C++, so it is much faster. And the sampling simulator is also re-implemented with an improved permanent calculation algorithm. So this is a usage example. It has a simple Python interface. You can define a simulator in the first line, which will simulate the quantum program, which is defined as follows, or on the third line. And you can just simply execute it, and you can visualize or you can see the results here. This is the result, for example, of a photon detector measurement or a particle number measurement. Yeah. So as I mentioned, you can choose your own framework for simulation. So for example, you can use the default calculator, which uses NumPy, SciPy, and Numba. But it doesn't contain automatic differentiation capabilities. But you can use also TensorFlow with Piquasso, which has also graph compilation and OpenXR support. So it is also fast, or faster than previous solutions with this. And one can also use JAX, which is another machine learning library, which also has OpenXR support. And that's why it's also quite fast as well. Now I want to talk about the Fock space truncation, because lots of photonic machine learning applications are implemented with Fock states. And Fock states have, I mean, you need to have infinite dimensions to represent a Fock state exactly. But in a classical simulator, of course you cannot. So that's why you have to truncate the Fock space. And there is a previous solution, which is called the local cutoff, which is implemented in another simulator, which is called Strawberry Fields, which is a cutoff on the particle number by mode. But what we implemented is that we use a global cutoff, which means that we cut off the particle number for the whole system, which yields vector sizes in general. And the argument is that, okay, we store less information in a sense, but this is more relevant information. So it has a higher probability if we use a global cutoff. So the contributions that are left out are still relevant, or not relevant. That's the point. So we compare the photon losses of Piquasso and Strawberry Fields. If we executed so it is a graph comparing the execution time and the photon loss of Piquasso, and one can conclude if you want to have, or if you want to allow for a certain photon loss, then you'd better choose Piquasso over Strawberry Fields because it has a lower execution time. And we also tested the automatic differentiation of Piquasso versus Strawberry Fields, and this graph shows that the automatic differentiation is an order of magnitude faster than with Strawberry field. It is because we use the graph compilation and the XML compilation support of TensorFlow, for example. And just to mention the Gaussian simulator capabilities, is that we have also implemented in the Piquasso Woods plugin the Hafnian calculation, which is the quantity which you want to use to reproduce the advantage scheme, which I have introduced before. It shows that our calculator or algorithm is much faster, or an order of magnitude faster than the previous solution. And we also have a web interface, which is made available at Piquasso.com. This is a circuit composer. You can arrange your photonic quantum circuit, and you can run it, and you will get results from it. So results like this, you can get the particle probabilities, but you can also get the Wigner function. You can also export the compiled code or the composed code into a Python code, and then you can run it with a simulator, which you can install with Piquasso. And now I want to mention some applications to Piquasso, because now it has automatic differentiation and fast algorithms, and we naturally want to use it for something. And the first application is the training of continuous machines. So what is a Born machine? Parameterized quantum circuits. So quantum circuits which has some parameters which you can tune, can produce probability distributions by using Born's rule. And this is an instance of generative machine learning, for example, because it technically generates the probability distributions. You can think of it as generative, right? But in photonic, you have continuous variables. That's why it's called CVBM, because continuous variable. It can generate position distribution, for example. As you can see it in this illustration, that you have these W weights in your quantum circuits. It's a single mode photonic quantum circuit, but you can use these weights. You have 5 weights, for example, and the position distribution, which comes out of or it doesn't come out of the photonic quantum computer, but it's sampled from the position distribution, which depend on these parameters or on these weights. Yes, but classical simulation of this is really demanding, even for a single mode. So previous solutions used or did simulations for a single mode, but were incapable of doing simulations for multiple modes because it was so difficult. But Piquasso implements a new classical algorithm for homodyne measurement. Homodyne measurement is the measurement needed for the position distribution. It is tailored for multimode system, which that it implements, and it has approximately 1,000 times speed up over previous solutions. And with this, we trained a multimode continuous variable Born machine with Piquasso. Here you can see the initial distribution. The first figure is the initial distribution. The second is the target distribution, which we generated from certain weights of you can see below. And we successfully trained this circuit to learn the distribution which was given to it. But for that, you needed to use many iterations, and you need to use many shots to calculate the gradient or approximate the gradient value. So it is really demanding, but yeah, it can do it. The second is that we can optimize non-deterministic gates with imperfect detections, or with perfect detections as well. Non-deterministic gates are in quantum computing or photonic quantum computing can implement qubits. So naturally, photonic quantum computers cannot implement qubits, but with this strategy of introducing some non-determinism into the calculation, it can implement, for example, conditional sign flip gates or nonlinear phase shift gates and so on. So what it says in this diagram is that if you have like an initial state, it goes through some circuit, which would depend on parameters, for example. Some of the modes in this circuit are measured and conditioned on the on the measurement. If the measurement is good in a sense, so if you detected something that you want, then you can look at the state, or you don't like it the state, but your state will guarantee to be something that is like that it implements something in a qubit-based quantum computer. So the U will not be a photonic quantum gate, but will be a qubit-based quantum gate, essentially. And we wanted to do this with imperfect detections, because photon detectors can have biases. So, for example, it can happen that in reality, you will have 2 photons coming into your detector, but the detector will only detect 1. 3 minutes. Okay. And yeah, and with these photon detectors in consideration, with these imperfect photon detectors, we can optimize the circuit, and we can show if we factor in these imperfections, we can achieve better fidelity or better success rate. It depends on what you need. So we produce this graph specifically to show that, for example, if you want to have like a 1.0 fidelity, you can have that, but it will have no probability essentially. But it's still, you can choose your fidelity or success probability with this. And you needed to use automatic differentiation for that in order to execute this circuit. Yes. And the last application which I want to tell you about is the gate synthesis with adaptive circuit compression. So the gate synthesis problem in quantum computing is that given a unitary matrix, find a corresponding circuit which implements it. So you want to decompose your unitary matrix to C-NOT gates or Hadamard gates or anything like that. Or in photonic quantum computing, you will have different gates. And there is an existing solution, which is based on optimization with universal layers. So you put together universal layers of photonic quantum circuits with some parameters, and you try to tweak the parameters in a manner that it will be like that you wanted. So it will be the given unitary matrix. And of course, you use automatic differentiation for this, and we use the jacks with X to get a 600 times speed up over the previous solution. And the speed up allows us to compress the circuit adaptively by throwing out gates which are close to identity. And it can be shown that if you do this many times, so if you do this throwing out of the gates, this compression, then you can reduce the number of gates in your circuit drastically. So you started with 150 or something, but you can reduce it to 25, which is a huge improvement over the original number, and it really matters in a circuit design. And the fidelity stayed approximately the same. So there is, of course, a trade-off. And this is another diagram which shows that there were many gates, but we were able to reduce it to not so many gates. So it is the orange is the compressed amount. So yeah, thank you for your attention.
Zoli, and time for questions.
Thanks. So, well, thanks for the presentation. I have a lot of questions, but I'll ask one. So basically, you showed an example for the Born machine. So can you use Piquasso then to, but also you show then other examples in which you trace the performance of your algorithm, whatever that is, in different cases, with respect to the simulator, the parameters you choose, for example, for the cutoff for the Fock states, or the presence of noise, or this flipping that you were taking into account in the measurement, or things like that. So the question is general. To which extent, so how configurable Piquasso is as a simulator, and can I use it to reproduce a different realistic behavior of the hardware to then understand the effect of my algorithms?
Yeah, so we can implement photon losses, for example, in Piquasso. These are deterministic losses, of course, but I mean, we can do that. We can also do the imperfect photon detection, but here you don't use imperfect photon detection. Here you would use something like imperfect homodyne detection, which introduces some noise into the position distribution. We can implement it, but it's not currently implemented as like a gate, like imperfect homodyne detection, but it's not that difficult to implement. So if you, I don't know, if somebody wants to work with us, or somebody has an idea to solve this issue, then we can, of course, implement it. So, but there are many things to implement in Piquasso and a finite amount of time. So we,
of
yeah,
course, that's always the case. But for me, it's a very important tool, because a lot of this, in our case, we had to stop this research because we did not have tools that we could reliably use. Like strawberry fields was too slow to do anything reasonable.
Yeah,
We'll talk.
Yeah, thank you.
Okay, further questions? Maybe you can keep it. You said that you have more questions. I cannot see any other raised hands. So
okay, so another question was very specific. You showed the plot where you have the choice of the global cutoff implementation on the Fox space. Do you have an idea of what yeah, you show those plots in which, yes, where you, and then the plot where you show the error, yeah, how the photon loss and the execution time changes. Do you have, for example, here you evaluated it over a specific network. Do you know what is the effect of the choices for this cutoff on how well or how easily the networks learn or converge or things like that? Effectively later on?
We didn't like compare like learning with Piquasso using this cutoff and learning with strawberry fields with that cutoff, but our intuition is that those or we saw the numerics, and those contributions which are left out are really small. So I wouldn't consider it to be like relevant for I don't know. I mean, maybe it could be that by those tiny little parts, it is more, I don't know, more expressive or something like that. But I find it, okay. I don't know.
It's probably depends on the use case on the thing itself.
Yeah.
But it's interesting.
But you can increase the cutoff in Piquasso as well. So you can, if you increase the cutoff with Piquasso, then you could actually contain the strawberry fields cutoff. But I don't know if that will be faster or not. Maybe it wouldn't in that scenario, because then you would have to, yeah, it's different. So I mean, depends on the use case, I think.
Okay, thank you very much. So I think we have to move on. So let's thank again to Zoltán. Let me call Bakó Bence, speaker from the same group, and Bence will speak about the problem-informed graphical quantum generative learning.